Welcome to the last session for today. So we have Parvinder talking about chaos in time, a dissipative continuous quasi-time crystal. The stage is yours.
Thank you, Itra. And first of all, I would like to thank all the organizers for bringing us together for this nice conference. And today, I'll be talking about chaos in open quantum system, and I will discuss what do I mean by this phrase chaos in time, and how it's related to the time crystals in open quantum system. So let me first give you an overview of my slides. So first, I'll be discussing the signature of chaos in both closed and open quantum system. And then I will tell you what do I mean by chaos in time, and then following that, I will relate it, how it's related to the time crystal in open quantum system. And I will use truncated Wigner approximation to find the stochastic trajectories which can be used to verify our results. And at the end, I will conclude. So let me begin with an example of this billiard boards. So we can, let's say if we have a billiard board which is of a regular shape, something like this, which is a circular. And if we have a ball which is moving inside this billiard ball without any friction, and then it's reflecting along the boundaries with a constant velocity, then usually this dynamics is very regular and it's very predictable. But if you put a very small kink into this spherical shape, then you could see that dynamics suddenly becomes very irregular, chaotic, and also not predictable after a very long time. And we can now look at the quantum analog of such billiard boards, and now you will see we can look at the eigenstate to distinguish them. Then you will see for such a regular shaped billiard board, you will see the similar kind of wave function, and in the chaotic billiard board, you will see the particle can be anywhere. So the probability of finding the particle is anywhere in this phase space. The other way to look at the chaos in a closed quantum system is by looking at the eigenspectrum of this of the Hamiltonian, and we can look at the level spacing. And for such regular potential, we will have a degenerate spectrum where the system follows the Poisson distribution, but for such a chaotic Hamiltonian, we will see the system follows the Wigner-Dyson distribution and have a level repulsion. These are like some signature of chaos in a closed quantum system. But now we can ask what happens if there is some friction in this case. So before the system explores the whole phase space, it will just dissipate. So if there's some dissipation into this case, then the system will go to a steady state before exploring the whole field space, right? And so now I will discuss what happens to the open quantum system in this context. So first of all, let me introduce the master equation in this case, where the first part is the coherent dynamics, and the second part gives the effect of the environment on your system, right? And we can vectorize this master equation in a larger Liouville space, where the vectorization of the density matrix can be written as a single eigenvector, and the effect of the dynamics is given by this Liouville superoperator. And this Liouville superoperator have a complex conjugate eigenvalues, where the real part is always negative to preserve the trace of the density matrix, and eigenvalues are complex conjugate to preserve the hermiticity of the density matrix in this case, right? And then these are the all the eigenvalues where the negative real part correspond only to the transient dynamics. And then there is this like a real part 0 and imaginary part 0 steady state, which is the stationary steady state of this open quantum system. But we can also have this purely imaginary eigenvalue, which correspond to the non-stationary state. And I will discuss how this relates to the time crystal and later to the chaotic phase in our case. So this is typically a spectrum of the Liouville superoperator in open quantum system. And similar to what we discussed for Hamiltonian case, now we can look at the spacing in the complex plane between these nearest eigenvalues and then of the Liouville superoperator. And then you could see, you can again do some spectral analysis in this case. So let me give you an example from this 2019 PRL. So this is like a XXG spin chain, which is driven at the boundary incoherently and also under collective dephasing. So in this case, the system eventually goes to a steady state, which is exactly solvable in this case. So for example, so system goes surely to the steady states and the transients are gone by the end of the, in the long time limit. But however, the eigenspectra, the eigenvalues of the Liouville superoperator shows going from, it can go from a Poisson distribution, which correspond to the integral case for the 2D complex eigenvalue structure in this case, to the chaotic case, which is the Ginevra ensemble in this case, right? So we see this signature of chaos in the Liouville eigenvalue spectrum, but the system still goes to a steady state. And now we are asking, yeah? Exactly, yeah, the radial direction. The radial direction, the nearest radial direction in this case. Yeah, you're welcome. Great, okay. Now we are asking this question, can we see? Now we are asking some questions in this paper, which are these. Like, first of all, we are asking, can we see steady state chaos? Can we see chaos in the steady state manifold instead of this transient dynamics, which correspond to the bulk of the spectrum in this case? And it means, like, can I have some observable, which does not which does not go to a steady state in time, but it makes a chaotic motion as we go in time, and keeps also keep making this aperiodic fashion even at the later time dynamics, right? And then how does it connect to the spectrum of the Levin-Zup operator, which I just discussed earlier, right? And third question is, what kind of open quantum system can have such kind of chaotic phase in the steady state, right? So I begin with answering the last question. We discuss route to chaos via the continuous time crystals in this open quantum system, because continuous time crystals are systems which are already non-stationary phase of matter in open quantum system. So let me give you a definition before I say more about it. So continuous time crystal are a system which breaks the time translation symmetry of the master equation. For example, this is a master equation which is a driven dissipative collective spin system, and this master equation is independent of time. So we might expect the system to go to a steady state in the longer time limit, and we can look at an observable. And indeed, for some parameter regime, for example, this omega by kappa less than 1, the system goes to a steady state in longer time limit, fine. But in this other parameter regime, when the drive strength is bigger than the dissipation strength, you can see the system start oscillating in time, in the thermodynamic limit only. And this breaks the continuous time translation symmetry of the master equation. So master equation expects you to go to a time invariant steady state, but the steady state is not time invariant anymore. So that's why we call it a symmetry breaking phenomena, and hence it's called time crystal in this case. So good. And now how does it connect? So first of all, how does this time crystal connect to the Levin-Zup operator eigenvalue spectra? So in this case, earlier we only had this one steady state, and now we see this additional purely imaginary eigenvalues coming up in the thermodynamic limit, which correspond to the frequency of oscillations of this mean field operator. So if we do a frequency for like FFT transform of this sinusoidal wave, then we will see the frequency that comes up is equivalent to the eigenvalues that are there, and there are like multiple of these eigenvalues equally spaced along this purely imaginary eigenvalue axis. So that gives the idea about the time crystal phase in open quantum system and how does it connect to the spectrum of the Levin-Zup operator. And now we propose that chaotic phase will look something like this, where the system is still breaking the time translation symmetry, but without any order. So you see a very chaotic dynamics. And then it should result into some eigenvalue spectrum in a sense that it's not equally spaced anymore. So you will see a random distribution of purely imaginary eigenvalues along this real zero part purely imaginary eigenvalue axis, right? And since it's a symmetry breaking phenomena which is breaking the symmetry but without any order, we call this as a quasi-time crystal phase, and it's a chaotic phase in time. So. And now I discuss our model in which we can see this kind of phenomena. So it's a model with two spin ensemble where there are two collective spin A and B. They are driven from outside and also coherent, and also talking to each other via spin exchange coupling. And then one of the spin is getting dissipated out incoherently, and the other one is getting incoherently pumped. So we have this model. And this model is able to show this kind of phenomena that I showed you earlier. So let me also discuss a slight more properties about this model. So first of all, let's take one of the limit where we put the interaction between two spin system to be 0, right? So let's say if you have two systems and they are not interacting to each other, then you see the dynamics of the two subsystem decouples from each other, and it looks like the earlier master equation that I showed that already can have time crystal phase. So now this system can have time crystal phase by tuning this omega by kappa parameter. And there's no interaction. So there's one mechanism to induce time crystallization, right? And now if we can put the drive is equal to 0 in this case, and we just talk about the coupling, and since there's like excitation difference between the system A and B, and when we couple them together, they start exchanging coupling, and only again, like in the limit gamma by kappa greater than 1, we get a time crystal phase. So this system have two different mechanisms to induce time crystalline phase. And depending upon what are the parameter regime, we can have different kind of time crystals. And now, when both of the parameters are non-zero, for example, when there is a drive and also coupling between these two spin system, then this creates a tension into the time crystallization because there are two different mechanisms trying to compete with each other. And this creates a disorder in the dynamics, which looks something this like this, and this becomes irregular dynamics in the time. And we see a chaotic system. But how do we quantify chaos in this kind of system? So first of all, we look at the mean field equations. And in the mean field equations, you see that we look at the dynamics of the rescale spin operator by neglecting any other like higher order correlations. And we get a set of coupled differential equation. And then we can use the Lyapunov exponent to characterize the different phases in this case. For example, the Lyapunov exponent here gives you the idea about how two nearby trajectory moving in time will diverge or converge. And for example, if the Lyapunov exponent, the maximum Lyapunov exponent is negative, then two nearby trajectory will converge toward each other, and that's a fixed point. And if the Lyapunov exponent is 0, you get a limit cycle case where two nearby trajectory will not go away from each other, but will keep rotating in phase space. And if the lambda is greater than 0, then any two nearby trajectory will diverge, and this is a signature of chaos. Okay, so we use this mean field equations and the maximum Lyapunov exponent. We plot it here. And then we get this complex phase diagram depending on what are the values of this parameter. For example, these two x's are the trivial one, which I showed earlier. So when the gamma is 0, then you see this melted case is we term stationary state, which was the time independent steady state as the melted case. And then if when gamma is 0, we can go from stationary state to time crystal phase as we cross this omega by kappa is equal to 1. Similarly, if we have omega is equal to 0, then we can have the similar transition in gamma by kappa, or gamma by kappa greater than 1. And then if we have small perturbation because of gamma in this side, then you will see the time crystal state is still stable for this one, and similarly here. And also, surprisingly, when they both are of the same strength along this axis, then also there's a new time crystalline order coming up. But the surprising thing is whenever you have to go from one time crystal phase to another time crystal phase, you have to always go through this chaotic phase. So this is the place where both the different time order phase trying to compete with each other and becomes chaotic. And let me show you so this different time crystal phase can be characterized by looking at around which average magnetization they are localized to. And then you can see they have different properties, this time crystal phase. And the black lines are the mean field equations in this case, in the thermodynamic limit. And all the colored lines are for varying system size. And you see as you increase the system size, you approach the thermodynamic limit. And in the actual thermodynamic limit, you will see this persistent oscillations is always there. And how do we characterize? So since I'm already showing you that there are like very large system size that we cannot exactly diagonalize, so we use truncated Wigner approximation in this case. So in classical, so in the mean field equation, we just assume like there's like a fixed point in the phase space, which time evolve according to the mean field differential equations. For truncated Wigner approximation, we consider fluctuation at the lowest order, where we assume a distribution around this fixed point, around a single point of the mean field. And then we time evolve all these different points using the stochastic trajectory with noises. And how do we do that for our system? So yeah, okay, I have time. So I can explain that. So first we convert our spin to bosons by doing the Swinger boson transformation. And then I can use this, I can replace the density matrix with the Wigner or quasi-probability distribution function and the action of the operators with the differential operator, and I can get a Fokker-Planck equation instead of the master equation, right? By truncated the higher order differentials in this case, and then we get a drift term and diffusion term, and the drift term correspond to the evolution of the mean field equations, and the diffusion term gives you the noise contribution, and now you can look at the average of this trajectories to look at the mean field values. So in this case, you can see the complexity is reduced by a lot because now system size is just a parameter, and now we can simulate for higher system sizes. So now I discuss the most important phase in this case, which is the chaotic phase. And as we could see, so I just pick one of the random points, but this will be true for any other points which are in this regime and this regime. So here you could see both system A and B are oscillating in time forever. So where the black are, again, the black lines are for the mean field equations, and then we show the transient behavior. The system is trying to approach the mean field limit as the system size diverges, right? So the system will always persist with this oscillation, but which are not ordered in time, and hence chaotic dynamics, right? And now we can look at the Fourier transform of this mean field of this dynamics, and then we could see that you see emergence of the frequencies that are not multiple of each other, and hence irregular frequencies appear in the Fourier transform. And since as the system size increases, you could see the peaks become sharper and sharper. And then we could see, okay, in the thermodynamic limit, you will approach the mean field equations. And now we can look at just at the mean field equation. So this plot is for the mean, like a Fourier transform of these two cases, but then this plot is for longer time, only for the mean field equation. And then you see delta peaks with irregular spacing. Then we ask, how does it connect to the Liouville superoperator eigenspectra, right? So this, as I discussed earlier, that in the time crystal phase, you see this periodic, you see this equally spaced imaginary eigenvalues coming up, which is equivalent to the Fourier transform of the frequency of the regular dynamics. So in this case, you will see unequally spaced eigenvalues coming up in the thermodynamic limit only, which are not multiple of each other. So here we can see that as we increase the system size, the system approaches the mean field dynamics, and the mean field dynamics have irregular spacing of the eigenvalues in this case. So with this, I will conclude my talk. Yeah, thanks. So just last message that for our chaotic phase in time, the only relevant eigenvalues are the dominant one, which close the spectral gap with unequal spacings, and the rest of the spectrum is not relevant to our steady state chaos. And finally, so I will conclude my slide. So we discussed a quasi-time crystal phase, which breaks the time transmission symmetry without any order, which is the chaotic phase now. And then with a minimal model of two-coupled spin system. And we have shown the stability beyond the mean field dynamics using truncated Wigner approximation. And it's a special kind of chaos since it's here in the 1D slice of this 2D spectrum. And it's neither Hamiltonian and then neither Lindbladian chaos. So that's it. Thanks.
Broadband as opposed to quasi-periodic, which is what this looks like. This looks like a sum of discrete frequencies not commensurate with each other, and that would make it quasi-periodic. But I thought that there were distinctions made between those two cases.
So yeah, okay, surely this diagram specifically is only for a finite time dynamics. Now, if you look at very longer time dynamics, like the lower one.
Well, I think if you look at short time dynamics, you can't tell.
Surely you can tell.
So you have broad peaks. That's a discrete spectrum or not. But if you run longer, I think in this model you even get sharper and sharper.
Exactly.
And so that sounds a little different from what you would, at least by some definitions of chaos, that's a different setting than pure chaos.
You mean like the nonlinear dynamical chaos or the quantum chaos in closed quantum system? Because they are also different things.
Including in the long time limit, you would not get line spectrum. You would get the continuous support of the Fourier transform.
Surely, I think you're right. Okay, so it also have this feature where if you're too nearby trajectories, they will diverge from each other, right? Okay. So because this irregular fashion that you see is there. So if you choose a slightly different initial state, then you will see after a time, whatever time period T, you will see a completely different state. So it's still, I will say, chaotic, and yeah, but okay. We can discuss later. Yeah, thanks.
Yeah, my question is regarding your definition of the Lyapunov exponent that you compute. How exactly do you define a Lyapunov exponent in this system?
So you can look at the perpendiculars. So you can look at the perpendicular distance between two nearby trajectories, and the divergence of this perpendicular distance. For example, like this distance here, right? How does this time evolve in the how does this change over the time? And if it just remains constant, right? Then
actually, let me rephrase. So how do you define these trajectories in this system?
Okay, so this is only for the mean field equations. So by just looking at, I choose any of the initial states, time evolve it, and then I choose a slightly different perturbed initial state, then I time evolve it, then I just look at the perpendicular distance and how does this trajectory evolve in time, and then you can find this by fitting this either divergence or convergence, you can fit this.
Okay, thanks.
Yeah.
Thanks.
Yeah, your system also has a gap. So if you, or what? How does the gap? Does it stay constant when you get make it larger and larger? You know, the eigenvalue of the image.
Of the spectra, yeah. So I have not
Yeah.
shown you the transient. So, for example, surely in this case, so you have some eigenvalue that is kept for finite system
Right,
size.
exactly.
Right?
Does that get closer
and
to?
this gets closer as the system size diverges, and then it can, like it's a dissipative phase transition, but not like a degeneracy of the steady state, but the steady state closes a spectral gap with purely imaginary eigenvalues, right?
But how does it scale? You know how this gap scales when increasing? I mean, does it go like
No.
1 over n or 1 over n squared, or does it go
Yeah, I think
exponentially small with the system size?
Okay, for time crystals, mostly scales with 1 by n.
Okay.
For time crystal phase, it scales with 1 by n. But for this case, it's, I think, scaling very slowly. I think like, we could not find the exact scaling because we could not diagonalize such a large Liouvillean, right? And it's also difficult to find out this random eigenvalues, and which one to trace is also a problem because every random eigenvalue will pop up in the thermodynamic domain, right? And then you don't know which one to trace and how this spectral gap closes. So this analysis is difficult to do in the Liouvillean operator for this case. For time crystal phase, it's possible because you know the frequency, and then you can keep track of that frequency. How does it close the spectral gap?
Yeah. Thanks.
Yeah, hi. Hi, Parvinder. Just a quick question. So the quantum model that you have of the two atoms that are combined, the two sets of atoms in cavities, if you just directly bosonize this and you try and take the classical mechanical model that comes up, like if you just pretend that this is classical mechanics just for a second, if you bosonized it and took the classical mechanical model, does that model look like a double pendulum or something where we expect chaos?
Yeah, okay, that's a nice interpretation that we could use, but we don't know exactly it maps to that or not, but surely it looks like, since we have when we have a single system, we have a periodic motion, which is simple like a pendulum, right? In the thermodynamic limit, the system say A, and then let's say if system B is also coupled to it somehow, then it slightly becomes chaotic. So
yeah, but I mean, it seems to me just looking that maybe this happens because of the gamma over S term. But I think you will have to actually check this to be the case, that if you, in fact, if you did the bosonization, the same thing you did in the Wigner truncated, but like directly to this, and looked at the harmonic oscillator models underneath, if the classical limit of it is chaotic, maybe it says something. I'm not very sure, but like I'm just asking as a question.
Yeah, thanks. That's, that's like a, yeah, I think so. This will come from this. Yeah, that's also true because without dissipation, it will be just like so then you don't know. So then with dissipation, you stabilize this limit cycle phase, right? So that's also important, and that's also brings us to that nonlinearity because of this collective interaction between the spin systems.
Let's keep the questions for later. And so this time
okay,
we're running out of time.
Okay. So
okay.
Up to you.
Hi, am I audible?
Hey, yeah.
Yeah. So I was just curious whether these OTOX can also be used in this case. Like there is also a connection with the Lyapunov exponent using the OTOX also. So can that also be used?
It can be checked, and yeah, we have not tried it because first of all, yeah, we are not, so since we need a very large system size, we needed this truncated ring approximation to do this, and then we have not looked at the OTOX in this case. But surely it can be checked whether the OTOX also find the same Lyapunov behavior or not for the system, but we have not explored in this case. Yeah.
Okay. Thank you.
I was wondering how crucial is this collective absorption in the B case? So
this one?
Yeah, the one that goes with the S plus. Yeah.
Okay. So yeah, so that's a very required thing because you see when I discuss this limit. So when I discuss this limit, right? If this is also S minus, then you will just lose the energy, whatever is there in the system, and you will go to a steady state. So you need to have some kind of mechanism to induce some excitation into the system. For example, for this case, this term is trying to take it down to the spectrum, right? But SX drive is trying to pump up the excitation, and this somehow in the thermodynamic limit is try to self-organize it in the limit cycles, right? In this case, this pumping is trying to give you the excitation that are required to sustain this phase. So you need this dissipator of S plus.
If you have pumping in both,
then it will thermalize to the maximum temperature, like the negative temperature state, because they both will, the excitation will diverge in both these cases, and you will again go to a steady state. Thanks.
Okay, thank you.